Today I have with me Dave Goldsman. He's a professor in the H. Milton Stewart School of Industrial Engineering, Industrial and Systems Engineering at the Georgia Institute of Technology. His research interests include simulation, output analysis, ranking and selection, and healthcare simulation. He was the program chair of the Winter Simulation Conference in 1995 and a member of the WSC Board of Directors between 2001 and 2009. He is currently a trustee of the board, trustee of the WSC Foundation. So Dave, I'm going to turn it over to you.
Thanks, Dave. Hi, everybody. Very nice to be here. I see that people are coming from all over the place. So anyway, maybe we'll get started. And I think what I'll do, I'll talk until people get tired. And if you have any questions, just write them on over, and Dave will forward them over to me. So today, we're going to be talking about sort of a very generic problem that is of some interest in simulation, namely selecting the best system. I'm going to be talking about the topic area mostly from sort of a statistics and elementary statistics point of view, but I'll try to tie it into different simulation examples as we go on. I forgot to do this already, but I'll send a copy of all the notes over to Dave, and he can forward them over to you folks. So you don't have to write everything down as I go on here. Now, you may see, I can't tell if you can see the entire slide, but you may see that there are a lot of pages on these slides. Don't panic. We'll adjust the talk so that it gets you out before 10 o'clock tonight. So anyway, you can see on the page there's my information, and feel free to email me or call me anytime you want. Here's an outline. I'm going to give an introduction to the problem of selecting the best system, just kind of put in context the kinds of things I'm interested in and what other people might be interested in. And then I'm going to go through three sort of generic problem areas, and I'll relate each one to simulation. For instance, finding the best normal population. By best, I might mean the normal distribution that has the largest mean. So suppose you're looking at three different normal distributions, and you're allowed to sample from each one, and you simply want to determine which one of these guys has the largest mean. Now, it sounds like a boring old baby statistics type problem, but in fact, it has a lot of applications in simulation. And I'll give some examples. Same thing with the Bernoulli distribution. You have 5 different competing Bernoulli distributions, and you might want to know which one of them has the largest p-value, the largest success probability. And there are a lot of real-life applications with that problem. People spend hundreds of millions of dollars on this problem, in fact. And then finally, I'll talk about this multinomial distribution cell probability problem. That sounds really a little bit out of left field, but even that has a lot of very nice applications that people use every once in a while. So, okay, so in general statistics and simulation as well, people perform experiments with the purpose of analyzing a system or systems. So you could be interested in you might want to know the characteristics of one particular system, and so you either simulate it or you take observations in some way, and you analyze the one system. I think the first example I always talk about is at the Guinness beer factory in the early 1900s. They were very concerned about quality control in their product, and so somebody had to obviously sample lots of the product, and they would take a number of readings, and then they would perform hypothesis tests to see if the beer was conforming to whatever standard they had. So that's analyzing one system. On the other hand, suppose you want to compare a couple of systems. Well, you have to do a little bit different tricks, and we'll talk about those in a minute. But in the context of simulation, you may want to compare a couple hundred different systems. Because simulations are easy to set up different alternatives. You just change a couple parameters, and maybe you want to look at a couple hundred systems. How do you do that efficiently? So it turns out, of course, that depending on what you want to do, you might have to use a different type of technique. when I took my first baby stats class, one of the first things they teach you is that when you're analyzing one system, like in my beer example, you could use confidence intervals. If you've had a statistics class before, then you probably learned about the t distribution, the normal distribution, and those are used to give confidence intervals on a particular parameter like the mean of your output. If I want to compare two systems, again, you could use confidence intervals from your baby statistics class, again, based on the normal distribution of the t distribution. But you might be able to actually do some clever little tricks. Some of you may remember what a paired t test is, or paired t confidence interval, where you try to match up observations in a smart way between the two competitors. So you might have, you might be testing, say, Coke versus Pepsi. Who prefers the two brands? There are different ways that you can conduct the sampling. If you want to ask 20 people, do you like Coke versus Pepsi? You know, that's one way to do it. You could give a score. How much did each person like Coke and Pepsi based on a range from 0 to 10? And you could get 20 people tasting the Coke, 20 people tasting the Pepsi, 20 different people, and you would get a total of 40 people to make your analysis on. Or you could use the same 20 people for both brands. And depending on how you do the test, one way may be much more efficient than others. Just out of curiosity, I'll see if we can use this hand technique here, the hand on the screen. How many people have heard of a paired t test or a paired t confidence interval before? Just really curious about this technology here. I'm seeing some actual hands here. Yeah. So if you've had a halfway solid statistics course, probably used this before. So yeah, very nice. Okay. Now the interesting thing comes about if the goal is to compare more than two systems, and then we have this analysis of variance that people take maybe in a second statistics stats course, and those are very nice techniques. Typically, those are used to test a very, very specific hypothesis. Namely, suppose you have 10 different systems, and they want to know, well, are the means of these systems all the same? If they're not all the same, the test is rejected. And of course, usually if you have 10 different systems, of course the means aren't going to be the same, and you end up rejecting the test, and you don't really learn too much except what you already knew. The means are going to be different. So ANOVA tests are very nice, but maybe there's another way to carry out analysis on more than two systems where you can get additional information. So the next sort of dimension of thought is, well, what do you even want to measure to compare different systems? So I've talked about a couple examples where we're interested in the means of the system. That's what we would use a t distribution or a normal distribution for. So I might be interested in which of the competing systems, whether there are two systems or 100, which one has the largest mean. I might also, if I'm a risk manager on Wall Street, I might be happy with different portfolios in terms of how much money they're going to get me on average, but I might want to minimize the variance because these days most people don't want to be on the roller coaster on Wall Street. They would prefer to make nice, even winnings and put up with a little bit of variation as opposed to going up and down and getting high blood pressure. So I might be interested in finding the system with the lowest variance. Or I might also be interested in finding the alternative that has the highest probability of yielding a success. So you could be simulating, say, 10 different possible inventory systems, and you might want to know, well, which system, which of these 10 is going to have the highest probability of making sure that I get a profit. My success is a profit. I want to know which system has the highest probability of making me successful. I might also be interested in the lowest risk, which is related to variance. I might also be interested in a combination of criteria. I want the largest mean subject to a variance constraint. I might have several criteria, and you might have to do some kind of Pareto analysis on the importance of the different criteria. So there's lots and lots of things to take into consideration. So what I'll do today is I'll go through and talk about 3 or 4 different problems and relate them to simulation. So the methodology I'm going to use is different than what we learned in our baby stats class. I'm going to do something called ranking and selection. This is a branch of statistics that hadn't really gotten a lot of play. It's been around for about 50, 60 years. But lately in the simulation literature, there have been a couple hundred papers in the last few years, and it's becoming a very nice, theoretically solid branch of both simulation and statistics. So I'll give you a couple examples related to the distributions that we had before. So it might be a little esoteric to find the normal distribution that has the largest mean. Well, maybe not. What if I'm interested in finding which of 10 fertilizers produces the largest mean crop yield? That's a normal distribution because crop yield is typically normal. So I always call that great expectations. And in simulation, we could be interested in which of 10 different queuing systems that I'm simulated produces the shortest mean waiting time. And I'll get into the fact that mean waiting times aren't normal, but I can turn this into a normal problem, it turns out. So anything involving these types of expectations, I can turn into a normal problem. Then I've got this, I'm reaching for a couple jokes here, but now I have this problem, great expectorants. Find the pain reliever that has the highest probability of giving cough relief. So that's an expectorant. That's actually a binomial problem. A binomial success probability problem. I want to find the binomial distribution that has the largest p-value, the largest probability of giving success. And people use these procedures all the time in clinical drug trials. And you could use this procedure, again, in finding the simulation that has the highest probability of building you a profit. And then, I was really stretching for a joke here, great expatriates, who's the most popular former New England football player? That, believe it or not, is a multinomial distribution. Find the cell of a multinomial distribution that has the highest probability of occurring. I'll give some more examples on that in a little while. Okay, now, since I can't hear anybody, let's have a show of hands to determine if these were good jokes or not. I really tried here. At least give me the pity hand. Okay, getting a few of those. Thank you so much, Dan. That's a tough audience. What can I say? So anyway, what I thought I'd do is I'll go through and talk now about each of these distributional problems in kind, and we can see what the procedures look like to solve these problems. And the beauty of this stuff is that every procedure that I'm going to tell you is almost trivial to invoke, and they make real good sense. And we're probably going to run out of time before I can do all 97 pages here, but you'll see that all the procedures are really easy to use, and they're more or less intuitive. Okay, so what I'm going to do, I'm going to talk a little bit about the types of procedures we're looking at in general, and what I'm going to do now is I want to find the normal distribution that has the largest mean. I'm going to do something called the indifferent zone approach, and you'll see why it's called the indifferent zone approach in a minute. Let me fill out the attendee list for a second. So my assumptions here are that I've got independent observations taken from normal populations. And you can see here that these YIs, these are just independent observations taken from the ice contenders. So I've got maybe 5 contenders, and Y51 is the first observation taken from contender number 5. And T is the number of populations that are competing against each other. And let's suppose that I don't know the means, because I want to rank them by the means. I don't know them. And let's just pretend for now that I have a known variance, although I can also have an unknown variance for these populations. So I've got T, maybe 5, maybe 10, maybe 20 normal populations, and I want to find the one that's got the largest unknown mean. Okay, it's a classic problem, very nice. How do you do it? I want to select the population associated with mean mu bracket t. And that bracket represents the largest mean. That's what's called an order statistic. So this bracket means the biggest of the competing means. I want to select the normal population that has that largest mean. If I do so correctly, by the time I'm done, I've made a correct selection. So my goal is to make a correct selection. Makes sense? I'm going to make that selection subject to the following requirement. This is called an indifferent zone probability requirement. I want to be correct. I want the probability of correct selection to be at least p star. I specify p star. It's like a confidence interval. Let's say I want to be correct 95% of the time. That's a good value for p star. Whenever this means the biggest mean minus the second biggest mean. Now, I don't know them, but if I'm the probability god, the probability gods would know them. I, as a user, do not know it. But I want to make a correct selection with at least 95% probability whenever the two biggest means happen to be delta star apart. So delta star might be like 1. And I'll give an example in a second. So I choose delta star. And it's kind of like a power calculation from statistics class. So my goal is I want to make a correct selection most of the time, 95%, whenever the biggest guy minus the second biggest guy is bigger than a certain cutoff point, delta star. And I'll motivate that again on the next slide. So the probability in that expression depends on the differences, ui minus mu j, because if they're all very close to each other, it's going to be a very hard task for me to make a correct selection. If they're very far apart, I'll easily be able to make a correct selection. It also depends on n, the sample size. The more samples I take, the better. It also depends on sigma squared. So if sigma is the common variance, I'm doing a very easy case here. If all the sigmas are the same and they're common, that will help. If some sigmas are bigger than others, the more variation, the worse you are off. So this constant delta star that I kind of glossed over can be thought of as the smallest difference that is worth detecting. And so if you choose a very, very small delta, that means that you want to be really careful so that whatever procedure you use, it will be able to detect small differences, the biggest guy versus the second biggest guy. If delta star is big and you choose that, then you say, well, you know, as long as the two best competitors are really far apart, that's the only time I really want to make a correct decision. You're not being so careful about that. That's fine. So if delta is really big, you say, well, as long as the biggest guy and the second biggest guy are pretty close, I'm not so concerned about getting the exact correct one. Either one of those will be fine. But if the two top contenders are very far apart, you definitely want to get the right one. So anytime that you have a configuration of the means, so this is the vector of the unknown means, if the biggest guy minus the second biggest guy is bigger than delta star, you say you're in the preference zone for a correct selection. It means I really prefer to be correct here. I want to be 95% sure that I'm going to get it right, because if they're bigger than this, it's a problem. On the other hand, if the biggest guy minus the second biggest guy is less than delta star, I don't care so much. I'm kind of indifferent which one I pick. So it's like two guys are pretty close to each other. Either one is fine. That's what that means. And any procedure that guarantees that probability requirement is called an indifferent zone probability procedure. So that's where the term comes from. Okay, there are hundreds of these procedures. A lot of people got tenure based on these procedures. The first one is from 1954. It's a single-stage procedure, and what that means is you take all the observations in one fell swoop, take the whole thing. There's a two-stage procedure 30-ish years ago by Renat, and that's very interesting because what you do, you take a preliminary sample, you assess the situation, then you take some more samples. And I'll go into some detail with that. And then there's a sequential procedure that reassesses the situation every time you take an observation. So it's a very, very smart procedure, and it really saves you a lot. Anytime you can reassess where you are, good thing. So let's talk about the single-stage procedure. It's really, really easy. And even if you don't understand my nasty notation from the previous pages, I'll just tell you in English what the procedure is. You enter into a table. You specify a couple constants, the number of competitors, T. You specify delta star, E star, and for this procedure, we assume that you know the variance, which not clear that would be true in real life, but we'll pretend it is here. And you enter the table with the T value, this delta star, and the P star, and it spits out the sample size that you have to take. Okay? In English, you take that sample from every one of your competitors. Say you have 5 competitors. You take the same number N of observations from each competitor in one fell swoop, and then whichever one has the largest sample mean, that's your winner. So the one having the largest sample mean probably has the largest mean, largest true mean, and that makes total sense. That's why you take the observations. So let's look at this a little more carefully. This says to calculate the sample means for each of the 5 competitors, each of the T competitors, and then whichever one gives me the biggest sample mean, that's the one I associate with the biggest actual mean. So all you have to do to run this procedure is look up N in my table and then take the N observations, which can be tedious, but you just do it, and then you take then you select the population that gives you the largest sample mean. Very, very nice. So here's the table. Obviously, I don't expect you to memorize this today, but you can see I have a T value, a P star, and a delta star value. I find the sample size from my table, and some of the sample sizes get pretty big, but see, this corresponds to T is 4 populations, P star is 0.99, which means I really, really want to make sure that I get it right, and this delta star is very small. It's a very small indifference zone requirement, so that's why I have to take 1,442 observations to get things right. Now, is that a lot? Well, in these presidential polls, people commonly take 1,500 observations before they can make a declaration as to which presidential contender is most popular. So, yeah, maybe 1,442 isn't that bad. Now, if you're running 1,442 simulations of each of the T systems, maybe that's a little bit of a hassle, but maybe not. And this is a very strict requirement. 0.99 is a very high probability. So anyway, if I'm lazy about using the table, I'm going to go very fast here. I can actually calculate N using this horrible-looking equation. What this thing is, this is a normal distribution quantile, but it's not the kind you can look up in the back of your book. This is a normal distribution quantile from multivariate normal distribution, and you need either a quick computer program or you need a really, really specialized table for this. So it looks like kind of a Christmas tree with all the superscripts and subscripts. So, you know, don't worry about it. I just wanted to impress you. And it turns out this constant is determined to satisfy what I call the least favorable configuration. In English, the least favorable configuration sort of means a worst case configuration to satisfy the problem goal that I have. I'm going to tell you, don't worry about that for now, but what it is, it's the configuration of all the contending means that minimizes the PCS, probability correct selection, yet satisfies this constraint that we had. Okay, don't worry about it, it's a technical condition. Okay, here's an example. Suppose I have T equals 4 contenders, and I want to detect the difference as small as delta star equals 0.2, so that's my indifference zone. And suppose I want to be correct with probability 0.99. Well, I go to my table, it tells me to take 361 observations per population, and I do it. And whichever one has the largest sample mean, that's my winner. If you increase delta or you decrease P star, you need a smaller N. And here's another example to show you what the consequences of that are. So if you want to save on observations, you don't have to work as hard. Okay, it's a very nice procedure, and it's robust, which means it works even when some of the assumptions are violated. And the reason I put this slide in here is because, you know, in simulations, you may know that if I'm simulating waiting times, I never, ever get independent and identically distributed observations. Waiting times are not normal. They're highly skewed. They're certainly not independent of each other. They're highly correlated, and they may change as the day progresses. Like I wait a lot less time at the fast food restaurant at 10 in the morning than I do at lunchtime. So the waiting time distribution actually changes. So if you want to use a procedure like this, how does it apply in simulation? Well, if the observations aren't normal, it turns out not a big problem. If you have exponential observations instead of normal observations, not too bad. If the variances between the populations aren't the same, sometimes it's a big problem. There are ways around it. You can use a different procedure. So it's sometimes a big problem. Dependent data, like correlated waiting times, that's a nasty problem. So you have, in order to use these procedures in a simulation environment, you have to trick the data into becoming normal, and there are ways to do that using batching, for instance. You can take a batch of correlated observations, and by a central limit theorem, the batches become asymptotically normal if the dependency structure isn't too awful. More on that a little later if we have time. I just wanted to show you very quickly a two-stage procedure due to Renat. And like I said before, the sampling proceeds in two stages. The first stage is just to make a guess as to what the variances are, and the second stage is to kind of wrap things up. You kind of see where you stand in the first stage, and then you take some additional observations to get your answer. So I'm going to just be very, I don't want to kill you with notation here, but here in this Renat procedure, it assumes that, just like with the T distribution from baby stats class, it assumes that the populations have unknown and potentially unequal variances. My Beckhofer procedure from the last page assumed everything was nice and the variance was known, and that doesn't really happen in real life. So just like before, I specify T, I specify delta star, my difference zone P star, my probability of correct selection that I want. I also have to specify how many observations am I going to expend in my first stage of sampling. Usually, I would recommend 20 or 30 observations, not just 2. And then I look up this constant, this mysterious constant, in a table, and I'll show you the table later. Notice I don't specify sigma, the various different variances, because I don't know sigma. I'm going to spend my first stage of sampling is going to estimate sigma. So here's the procedure. I'm going to take independent and identically distributed samples from each population. Notice that the sample size is n0, just like I specified. I calculate the sample mean from each population. I calculate the sample variance from each population based on the first stage of n0 observations. Don't be intimidated by the notation. It's not a big deal. Okay, then I calculate the sample sizes that I'm going to need to finish the problem up. So I've taken n0 observations already. This is telling me how many additional observations do I need to take in my second stage. Actually, it's ni minus n0, because I've already taken these. Without going into tedious detail here, the proof is straightforward, but it took people 20 years to figure it out. If the variation of population I goes up, that's bad. That means I need more observations. If delta star goes down, that's bad. I need more observations. So depending on how SI turns out, if the variation is big, I need more observations. If I specify a small delta star, I need more. In any case, this NI tells me how many more observations do I have to take to get my question answered. So how do I do that in the second stage? Now, I take all the NI observations, calculate the grand mean for both stages, all NI observations, and whoever has the biggest sample mean, that's my choice for the largest true mean. Very, very easy. Without going into detail, I can also give you a confidence interval here on how much better the best is than the others. This is called a multiple comparisons with the best. I put this on here simply as a bonus, and you can take a look at it if you have some time. So again, the procedure just says whichever guy has the largest sample mean, that's the winner. It makes total sense. Okay, I'm going to now here's the table. This is what the table looks like. It's already made up for you, so you don't have to do it yourself. I'm going to give a small simulation study that we did a long time ago, just to show you how you would use this in the real world. Then I'll talk about a couple other problems. Suppose we have 4 different airline reservation systems, and we want to know how long does it take before the system breaks, before it fails. We want to know the expected time to failure. We're interested in finding the system with the largest mean expected time to failure. And we'll call that mu I for system I. I goes from 1 to 4. We know, past experience, let's say, that these expected times are roughly about 70 days for each of the 4 competitors. So that means that allows me to choose my delta. I'm going to say delta star is about 2 days, 3,000 minutes, because to tell you the truth, it doesn't matter if the system fails 70 days, 72 days, 68 days, it doesn't matter to me, as long as they're within 2 days of each other. So let's select the best system. I want to get probably at least 0.9, and I'll make delta star equal to 3,000 minutes. Now, the problem is I can't use queuing theory here. The systems are too complicated. I'm going to let Tij note the observed time to failure when I run my jth replication of system I. Tij is absolutely not normal. It's some skewed distribution because these failure times are never normal. However, since I'm running independent simulations, running replications, at least they're independent, identically distributed, but they're not normal. In fact, they're highly skewed to the right, like these times to failures always are. So what do? Well, instead of using these raw Tijs in my procedure, what I'm going to do is I'm going to take batches of these. I'm going to run multiple micro replications, I call them, and I'm going to make lots of these Tijs, smush them all together. So here, this is what I'm doing here. I'm running lots of Tijs. Don't be intimidated by the notation. I'm going to turn this into one Yij. If I run the system I run several simulations. I take the average, and that gives me something that's approximately normal. Eij is the number of replications in one of these batches. So I run several BI of them, and I get something that's approximately normal by the central limit theorem. It's very nice. So again, these estimators, these YIs, are approximately IID with independent identically distributed with expectations mu I. If I take enough replications, then they're approximately normal. And that's great. And in this case, I made no assumption about the variances, so I can go and use my procedure now. So what I'm going to do, the first stage is going to be a pilot study. Isn't that funny? Pilot study for airline reservation systems. I'm going to run each of the systems for 20 macro replications, each of which consists of 20 simulations per batch. And I'm going to run 4 of them, 4 systems, E star 0.90, and it turns out if I go to my table from a few pages ago, H is 2.72 if you care. So here's what I get. I'm just going to give you the results from the table. This is my first stage sample mean. Remember, larger is better. So system 1 fails on the average for my 20 replications, 108,000 minutes, about 73,000 days, 73 days. System 2, 107 minutes. System 3, 96. System 4, 89. You can see they're a little bit different. The problem, though, is that the standard deviations of these estimators are just really big. So 108,000 with a standard deviation, 29, that doesn't really tell me a lot. So that's why I've really got to take more observations. When I plug into my handy-dandy formula for N, it says, well, take 699 of them, 699 more observations. And that's because S is so big. Right here, system 4, S is not very big. It only tells me to take 356 additional simulation runs. Well, by the time I do that, let's go now here. I've taken 699 more. The first system has a mean time to failure of 110,000 minutes. The last system, 86,000. But look at these standard deviations now, much smaller. And I can tell statistically that system 1 is, in fact, the best. So the darn thing worked pretty well. And I happen to know, because I ran the simulation myself, system 1 is the best. In this one time, I was right. Very good. So that's a nice example. I think what I'm going to do is I'm going to skip ahead, skip, to some comments on normal extensions. And what that means is what else can you do? You can have correlation between the competitors, like a paired t-test. You can have extremely efficient sequential procedures. The Renat procedure only had 2 stages. I can make multiple stages. It's a lot faster. I can eliminate populations that aren't competitive. I mean, suppose I saw that some of the simulations were just trash. They weren't doing any good. Why even bother running any more of them? And so I would just stop running them and be more more efficient in my simulations. I could also do, instead of my usual variance estimators from maybe stats class, I could use other ones, but that's another issue. So now I'd like to show you a problem involving the Bernoulli distribution. How do I find the best Bernoulli distribution? This is a wonderful problem, very useful. Example, which of 5 different anti-cancer drugs is the most effective? Which simulated system is most likely to meet your design specifications? Which simulation will most likely get your order out on time? Which inventory policy is the best? I mean, all sorts of things like that. Again, hundreds of such procedures. I'll show you, I think all I'll have time to do today is just show you the single-stage procedure of Sobel and Hoyt from the late 50s. It's very, very nice. And I'll use the indifferent zone approach again. And you'll see it's quite simple to use. Again, what you do is you're going to take a bunch of observations, and whichever population has the highest success rate from your observations, that's clearly the one you keep. It makes sense to me. So here we go. And again, I apologize for the notation, but it's not so bad. So you have 2 competing Bernoulli populations with success parameters P1 through PT. This means my first anti-cancer drug has probability P1 of curing me. My last one has probability PT of curing me. I do not know what the P's are, but this is my talk, so I can make whatever notation I want. Whatever these ordered P's are, the little brackets mean this is the order. Whichever Bernoulli I pick, I really want it to be the one with the largest proportion of successes. So I don't know which one it is, but I want it to be this one. So we're going to pick the one that hopefully gives me that. Here's my probability requirement. It looks a lot like the other one. I want to make a correct selection with probably at least P star whenever the difference between the best guy and the second best guy is at least delta star. I'm using capital delta here because it's a little different than the one from before in that this has to be constrained between 0 and 1, obviously, because it's these are probabilities. So you choose this just like before. P star should be fairly large, especially if it's a cancer drug, and delta should probably be kind of small. If one cancer drug has a probability of 0.9 of working and the other has a probability of 0.8, I really, really want to catch that. Now, if something's 0.9 versus 0.895, doesn't matter. I mean, they're pretty much the same. Maybe one of them's too expensive. I don't know. But if there's a small difference, I don't care so much. If there's a big difference, I really want to catch it. Okay, again, this indifference zone probability requirement just means it's the smallest difference that I deem as worth detecting. Okay, and of course the probability depends on what are the probability of success. The correct selection depends on the probability vector and how many observations I take. If I take more observations, I'm going to do better. Okay, so here's procedure Sobel-Hoyt. Again, all it involves is just looking something up in a table. Very, very simple. And I'll show you how it runs. I specify delta star and P star just like before. I go to the table. I'll show you what it looks like in a minute. And then it says, okay, take 15 observations from each of your cancer drugs. So suppose, I have 5 drugs that I'm comparing. I take 15 observations, take 75 in total, and I look at I look at the drugs and how they have whatever their cure rate is for each one. Suppose the first drug, 10 out of 15 are cured, and the others don't do so well. Maybe the 5th drug has only 5 out of 15. Well, clearly, I'm going to take the one that had 10 out of 15 that did the best. The nice thing about that is the 15 is determined by me looking that up in a table. So people use this stuff all the time in helping to design clinical trials in the drug industry. They might not use this particular procedure, but there you go. So here's the procedure. Add up the number of successes. Whichever had the highest number of successes, that's the one that you pick. Now, since it's a discrete problem, if there happens to be a tie, suppose 2 of the drugs gave you 10 out of 15 wins, then this is going to sound awful, but if you really need to tell your boss an answer, you just randomize, pick one. That's not a real satisfying thing to do, but and it doesn't really happen that much in practice, but that's what the procedure says to do. Okay, here's the table. I'm sure you'll all want to memorize this. It's going to be a bestseller someday. But you can see as I increase P star, I have to take more observations. You can see it goes from left to right here. As I decrease delta, I take more observations. And it turns out as I increase the number of competitors, I also turns out take more observations. So it's a nice procedure. It's the first one that they had. Here's an example. Suppose I want to select the best of T equals 4 treatments with probability of correct selection at least 0.95 whenever the difference is at least 0.1. So now I don't know this difference, but what I'm saying is if the difference happened to be 0.1 or more, I really, really, really want to get the right one because it's going to kill people if I don't. So I go to the table. You just read the table. I could go backwards, but I'm not. And it says take 212 observations. And then let's pretend at the end of sampling, the first drug had 70 cures, the second one had 145, the third had 95, the fourth had 102. Well, look at this. Clearly, I take 145. Drug number 2 was the best one. That's kind of nice. All right. Well, now I'm going to I'm just skipping over one of the procedures and talk about some Bernoulli extensions. Suppose I could correlate between populations. And similar to the paired t-test, that would help. There are some extremely efficient sequential procedures. There's actually an optimal one. And again, eliminate populations that aren't competitive. So if you see that a clinical trial is revealing that your particular drug is just no good, don't use it because you're killing people. So have that drug drop out of the clinical trial, use a good one. Similarly, if you see that one of your simulations is just yielding, suppose you're looking at certain inventory policies, and one inventory policy is just not competitive, it just doesn't work very well, why waste time simulating that anymore? Get rid of it and concentrate on the good guys. And so these are obvious extensions, and people do research on that. So it looks like I'm going to spend about 8 to 10 minutes now on multinomial distributions because I think it's a cool distribution. And these are things like, suppose you have a number of different categories, and you want to find sort of the most popular of those categories. In particular, who's the most popular political candidate? You know, suppose 3 people are running for president. Which one has the highest probability of being selected by a particular person? Which TV show is the most watched during a particular time slot? Although, of course, with cable and TiVo and things like that, it's becoming harder to tell what a time slot means. In simulation, which simulated warehouse configuration maximizes throughput or has the highest probability of delivering the proper throughput? These are all examples of multinomial observations. And again, I'm going to use an indifferent zone approach in attacking this problem. Now, since some people, maybe I could have a very quick show of hands, how many people have done anything significant with multinomial distribution before? Because I know it's a little bit unfamiliar in stats class, so let's see, Tom has, and a couple other people raising their hands. It's sort of a tricky little distribution, but it's very useful. So the experimental setup is this. Let's suppose I have 10 T different categories or possible outcomes, 3 different TV shows or 5 different political candidates. P sub I is the probability of the ith outcome being chosen. I have to add up to 1 since everybody has a favorite. And let's pretend I make I take n observations, and let's let y sub I be the number of outcomes that fall in category I after you've taken n observations. So y sub I might be the number of times that, let's say I chose Obama after I asked 1,000 people. So I'm just making that up. There's no political thing intended there. So it turns out that the vector y1, y2, yt, so this is how many people chose Obama, how many people chose Romney, how many people chose another candidate after a certain number of observations. It turns out that's the probability mass function. That's a multinomial distribution with parameters n and p. And you may recognize this, believe it or not. It's actually similar. Don't worry about how it looks. It's actually similar to a binomial distribution, multinomial. More than having a success and a failure, you have all different categories: Obama, Romney, and whoever else is running. Okay. Example: suppose 3 faces of a fair coin, a fair die, are red. 2 are, I think, blue. I can't see it. And 1 is green. So here are the different probabilities of the 3 colors, 3, 6, 2, 6, 1, 6. I toss the coin 5 times. The probability of observing exactly 3 reds, no blues, and I guess 2 greens is this. I just plugged into my equation. Turns out it's 0.03472. It's like a poker problem almost, a little bit like a poker problem. And you can calculate this by using my equation from the last page. Very simple, just plug in. Okay. Now, I'm interested in, suppose I didn't know the probabilities 3, 1/2, 1/3, 1/6 from the previous example. Suppose my goal was to choose the most popular color, the most probable color, which between you and me we secretly know is red. Okay. Here's my rule. For whatever reason, suppose I choose, what I'm going to do is I'll take 5 observations, and I'm going to choose the color that occurs the most often. I'm going to use randomization to break ties. That's my rule. I'm going to take 5 observations, 5 simulations. Whichever one wins the most, that's going to be my most popular color. I hope I'm right. So let's see what we get. I'm going to let Y be, this is the vector of the number of reds, the number of blues, the number of greens that I see in 5 trials. Now, don't worry about this. This mess right here is the probability that red wins in 5 trials. Remember, we secretly know that red is the most popular, the most probable color. I think it's probability half. I can actually go and calculate this probability that red wins. This is what we would call the probability of a correct selection if my rule is to just take 5 observations. So here we go. Let's do that. Made a little table. Don't worry about the table, but this is what it turns out to be. It turns out if my rule is to take the color that wins the most often and say that's the right one, I can calculate the probability that red wins, the probability of correct selection, is 0.6042. Notice I have these 0.5s here. That's for randomization. Don't worry about it. So the probability of correct selection, if I take 5 observations and pick the most popular one, is 0.6042. I can increase this by taking more observations. So if instead I took 20 observations, this probability would go up. So with that in mind, I've got just 3 or 4 minutes. I'm going to just show you a procedure. One last thing. Forgot about this. You may not be interested in finding the most probable alternative. For instance, if I have 2 inventory policies, A and B, the profit from A is $5 with probability 1. The profit from B is $0 with high probability and $1,000 with probability 0.01. It turns out it's very easy to show that 99% of the time, A is going to be better than B. Just by the way I've defined this goofy problem. Yet, the expected profit from A is less than B. So you as a manager have to decide what's more important, the probability of being more popular or the probability of having more profit, the expected value. So are you going to win every once in a while really big, or are you going to win most of the time? These are 2 different measures, and you have to decide that. If you like this probability thing, then multinomial is for you. Okay, so one minute per slide here because I know people have to go in a minute. Here's some of my assumptions. This is a multinomial distribution. If my category I wins, I give it a 1. It wins. If not, I give it a 0. The unknown probabilities, I order them from smallest to largest. I want to select the most popular candidate. So, for instance, if Obama was the second candidate, he would correspond, in this case, to the largest probability of popularity. What I do is I take these wins and losses for each category, I add them up, and whoever has the most wins after M observations, that's my overall winner. And I have just enough time to show you how these things work. I want to select the probability associated with the category associated with the highest probability. If I do so, just like before, I make a correct selection. I want to make a correct selection with probability, say, at least 95%. Whenever, instead of a difference, now I have a ratio. It's called a ratio estimator. Whenever the biggest probability divided by the second biggest is at least some number theta star, some number greater than 1. And this now is the smallest ratio worth detecting. So if I can do that, then I'll be very happy with my correct selection. So here we go. I'm just going to show you the single-stage procedure of Beckhofer. It's very easy. I specify T. I specify my indifference zone requirement, my P star. I look up N in a table, just like before. I take observations, I add them up, and whichever one, don't worry about this least favorable configuration stuff, but whichever observation has the highest, that's the one I pick. That category is the one I pick. And here's an example. Whoops, let me click back up. A soft drink producer wants the most popular cola product, and I think there's 3 of them. Actually, I can't see this stuff on the right. The company will give a taste test to N people. I want to know what sample size do I need to pick the best of the 3 colas with probability correct selection at least 95% whenever the ratio of the biggest probability to the second is 1.4. So if one cola is ahead of another by 51, 49%, that's not within 1.4. I don't care. That's fine. But if one is like 60% to 40%, which is a ratio bigger than 1.4, I really want to catch that. So I go to the table, which I'll show you in a minute. T equals 3, P star 0.95, theta star equals 1.4. Let's go to the table. 3, 0.95, 1.4, 3, 0.95, and 1. It tells me I need to take 186 observations. I ask 186 people what their favorite cola is. Whichever cola gets the most wins, that's the winner. And you can see it's very intuitive. Whoever wins the most wins the whole competition. So I'm going to skip all the way to the end, just talk about some extensions. Again, I can do sequential sequential procedures very easily. The extensions could be, I can use these for non-parametric simulation problems. We have now an optimal procedure, which does sampling extremely efficiently, and procedures that are adopted for different costs of observations. So with that in mind, maybe if anybody has some questions, because I know I'm starting to run out of time here, I'd be happy to field them. And if not, you can always feel free to email me or give me a call. Anything would be great.
Thank you, Dave. Yeah, well, we'll wait a minute for some questions to show up. Usually takes people a moment to get their typing in up there, so we'll wait for some questions. But thank you very much, Dave. This is really helpful. It's given me a lot of ideas myself as a simulation software developer, thinking, gee, we should do more of this stuff. So
it's pretty easy to implement these procedures too. I mean, you don't have to do any programming to some extent on some of the procedures. You just have to run them. That's all. The simulation would be very helpful because it would tell you how many runs to make and then maybe automatically do the runs.
Yeah, that's what I was thinking of. That might be a nice thing to add in. So, are there any questions? Type them into the question box, and I'm sure Dave will be happy to answer them.
Yeah, it was certainly very nice to talk to so many people. Very, very nice. And like I said, if anybody needs me for anything, I'd be very happy to interact with you.
We got a good question here. Does this relate to the field of order statistics?
Oh, absolutely. Yeah, most of the proofs involve some manipulations with order statistics. In fact, some of the guys that did the original work in the 1950s were very, very good friends with some of the pioneers of the field of order statistics. Yeah, they're intimately related. Every proof has order statistics in it, much to my dismay because they're tough to work with.
Okay, I'm not seeing anything else, so thanks again, Dave. I hope everyone has a good day, and we'll see you again on April 11th for talk with Ed Williams. Thanks again.
Thanks, everyone. You'll like Ed. He's a good guy.